Hello everyone. So in the continuation of CTQ 12, we are on the part 3 where we will discuss about the impedance calculation with the input impedance or output impedance with both ideal and practical cases what we have. And we will try to use the negative feedback concept also. And before that, I will discuss whatever we have calculated, the simply the gain values for these two structures by considering means infinite gain or can say ideal case, and also if the finite gain is there, then what will be the expression? Just we have to recap it. Okay, so for this first structure, that gain is a, and from here we can simply write the equation, because for this amplifier what we have to see is gain times the difference voltage, which is nothing but a V positive minus V negative equal to V out. Simply we can see V out equal to minus a Vx, and after that we can write the expression for the KCL at node, what means so node X. Okay, so we can see the current entering in this node X is nothing but Vn minus Vx by R1, and that same current is flowing through this R2. I'm expecting that there is a no current going inside this op amp, because it's op amp, we know it is designed by some high impedance devices inside it, mainly called like MOS devices. Okay, so this is the current equation, and from this current equation, if I am considering the A properly here, then the final expression that we get here is V out by E in is minus AR2 1 plus A times R1 plus R2. If A is much greater than 1, that we usually consider that your gain of the amp here is very high, which is usually we say means order of 100,000 or sometimes 10,000 also. So from there we can see the expression reduces to that. Okay, but after that we say ideally that gain is infinite or very high, then we can have the expression direct minus R2 by R1. This is the general expression that we see. But if there is a means some finite gain is available, let for the time being, if I consider the example, if everything is like gain of your amp is given 10, and what you mean to say, R1 is my like say 10 ohm, and R2 is also called 10 ohm, then this expression cannot be true. Minus R2 by R1 is not true. In that case, V in my V is 2 comes to be minus AR2 is 100, and divided by 1 plus A, which is nothing but 11 times 10 plus R2 is 10. Okay, so this expression nearly comes to be minus 10 by 11 plus 1, which is nothing but minus 10 by 12. Okay, which is not equal to minus 10 by 10, which is nothing but a minus R2 by R1. Okay, it is not equal to this value. So we have to be careful when there is a finite gain is given. Okay, when there is finite gain, we have to be very cautious while we are calculating anything, whether it is a gain or it is an input output impedance. We must be careful for that. Okay, and we can simply write the KCL equations, and one relation, this relation is directly nothing but for the output of amplifier is nothing but the difference voltage times the gain. And what is the difference voltage? Difference voltage is nothing but V positive minus V negative times gain is a, this is a difference voltage. Okay, so this is the gain expression we directly write every time. Okay, now come to the second structure. This is your non-inverting amplifier, and for the non-inverting amplifier, again we will see the V out is written as nothing but 8 times the difference voltage. Here the difference voltage is V in minus Vx. Okay, so V in is involved in the difference voltage, so there is a voltage mixing is happening, that I already talked about it in the previous video. Okay, so it is a V in minus Vx, which is the difference voltage. So this is the one equation that we are using for the V out, and other equation is we simply use the KCL at the node X, what we have done for the previous example or the previous circuit. Okay, so from here I am calling this R1 by R1 plus R2 as a beta also. This reason I told you previously, because here is a voltage sampling is voltage mixing is happening. So what we can say, the X node voltage is nothing but a feedback voltage that we are getting. Some part of output is coming back, and we are feeding this difference to the amplifier. So the already I drawn the circuit on the previous video. Okay, in the previous video. So this term can be called as a beta. So finally we can write the expression that is a beta V out. From here we can see the V out by V in comes to be A divided 1 plus A beta. That is the general expression for the closed loop gain, which is nothing but a open loop gain divided 1 plus open loop gain times beta. Okay. So again, if I consider A to be very much greater than the 1, then we can say this expression reduces to 1 upon beta. And beta is simply R1 divided by 1, R1 plus R2. Then 1 upon beta is the reverse of it. So simply we'll get this expression. This is the general gain we write. But now, if gain is finite, then we cannot write always like this. Okay. Again, if I say my gain is 10, simple same example. My R1 is 10 ohm. Okay. R2 is also 10 ohm. Then what it comes to be? The V out by V in the closed loop gain comes to be A divided by 1 plus A times beta. Let's say beta is, or not say, the beta is here R1 by R1 plus R2, which is nothing but 1 by 2. Okay, so it comes to 1 by 2, 5. So 10 by 1 plus 5 is nothing but 10 by 6. So it is not equal to your general expression 1 upon R2 by R1. Because what is this? It comes to be 2. Or what is this? It is less than 2. Okay. So what we can say, when gain is finite, gain is finite means open loop gain. When open loop, if open loop gain is finite, closed loop gain is different standard gain expression. Standard gain expression for non-inverting structure. For non-inverting or either inverting amp gain expressions. Okay, so generally we see the gain expressions as minus R2 by R1 and 1 plus R2 by R1. So they are like not matching with that. Okay, here gain is finite, then we can see what we gain we are getting is less than 2. Here also what we are seeing, it is not exactly minus 10, or it is not exactly, sorry, it comes to be minus 1, but it is less than the minus 1. In terms of magnitude, what we can see, if A is finite, okay, it is called the open loop gain is finite, then closed loop DC gain comes less than the closed loop DC gain when open loop DC gain is infinite. So when we are considering the open loop gain, this is magnitude I am talking about. So when open loop gain is infinite, or we are considering the ideal M, then what gain we are getting here is a minus 1, or magnitude it is a 1. But what about when we are considering gain to be finite, which is 10 here, then the closed loop gain we are getting 10 by 12, which is less than 1. Okay, here it is also happening. When open loop gain is finite, which is 10 here, then closed loop gain is less than 2. Rather, here we can see it is 2. So we can say the magnitude of gain or closed loop gain when open loop gain is finite is less than the magnitude of closed loop gain when open loop gain is infinite. Okay, this is the only point I want to make here. Now let's come to the impedance calculation, what we can do. So let's consider the first structure, inverting amp. So here we have two things. We can apply one thing direct, we can apply a test source at a point of input. Okay, so we can apply a test source and we can find out what the V2I IT ratio is there. Okay, so at V in point, I can apply test source. I can observe the test current. Then R in at this point is simply VT by IT. This is the one thing. Okay, so this thing can also be done. Next thing, the other thing, what I can say, this is my R1, and here is my input. If I know the input, this what I call, let's say, small rn. If I know rn after that, then what can be there? Okay, if I know the r in after this point, then what can be there? This is r2, because we have to anyway means use lesser calculations. So if I know the impedance at this node, then simply I can say what I can say, rn, the capital rn is r1 plus small r. Okay, so either I know Rn, then I can calculate the capital Rn, which is nothing but input impedance from the source. And if I directly want to apply the test source at the place of input, then also we can find. So I prefer this thing, the second case. This is my case one, and this is my case two. Why I prefer this? Because I involved with the less variables, which is because R1 is already out. Okay, so let's proceed with this first, and then we'll see the previous one. Okay, so if I'm applying a test source directly here, yeah. So if I'm applying a test source directly at the input of amplifier, which is the inverting terminal, this is 0. And if I'm applying a test source directly here, BT, and here is IT, and R2 is still there, V out. Why I'm writing V out? Because I have to use this node voltage expression. That's why I'm continuously using it. Okay. So because we need to involve V out in the calculation, directly we can write this is a minus A times your Vt. This is the one equation that we can use. Okay. What extra? Other equation is simply I can write It as Bt minus V out by what I call R2. Okay. This is the second equation. Another KCL at node, inverting node. Okay. So one thing here that there is a no current going inside. Whether the gain is finite, whether it means input impedance can be there, but it is very high usually. We design it at the design level. We can say the input impedance of amp is very high, op amp is very high. So I'm considering there is a no impedance, no current going inside this amplifier. So only the current IT is there, and that IT is flowing through the R2 and going to the output of this amplifier. Okay. So from here, what we can see, IT equal to BT plus ABT 1 plus AY R2. So BT by IT comes to be R2 by 1 plus A. Okay. So if the gain is very high, let's say gain is very high, or mean to say gain is very greater than 1, and what it can be? It can be simply written as BT by IT equal to R2 by A, and even I can say if my gain is infinite or very large, and it comes to nearly 0. Okay, so what is the R in then? R in then is what? R in an ideal case comes to be R1 plus let not ideal, but if my practical amp is there, gain is there, then this is the complete expression that we'll get here. Okay, and if my A is infinite, then we simply get the R1 as a input impedance. Okay, so this is the case when my gain is infinite. Okay, so we need to capture these all means what I can say, these parameters in the calculation when we are dealing with some practical structure. For example, what example we are continuously taking? If my A is 10, R1 is 10, R2 is also 10 ohm, then what is the input impedance? Input impedance is nothing but R1 plus R2 by 1 plus. So it comes to be nearly 10.09 something order. Okay, it is not directly equal to 10. So when the case is like that, so we cannot directly say that R1 is the only input impedance for the structure. Rather, there is some additional term which is nothing but R2 by 1 plus A. Okay, well, this is the usually way I follow, because we know that from here the calculation are less. There's only two equations directly you can find. You can write the V out as a minus AVT, but here also we can apply. Let apply here. So this is A, gain is A, and if I'm applying test source here, which I call VT, and IT we are capturing or observing. And again, I am using the V out because V out will come into my expression of equation, means in the equations. So what can we write? A simple one equation is very simple. Let's call this node at X. Then what is this? V out equal to minus AVX and it equal to Vt minus Vx by R1. So here what we can see in these two equations, there are four variables. One is V out, other is Vx, third is it, Vt. But what I want the relation between these two. So one more equation I require. The other equation is that it is also equal to Vx minus V out by R2. This is the third equation. So if we'll use the three equations for finding for correlating four variables, then obviously we can get the relation between any two. Okay, so I can get the relation between it and vt. I will not solve it. You solve it and check it out. But I prefer this because I can handle it in the two equations. Okay, so two equations are here. Easy. So what should be your preference? Lesser the variables coming in your calculations, easier will be the calculation. Because sometimes you cannot directly say that okay this is happening, because if someone is giving you the finite gain amplifier, no, you cannot directly say that my input impedance, if I am looking from the source, is the R1 only. It has some additional terms also, and you find the point or place of the calculation where you can have the lesser calculations. In my case, the second structure, if I calculate the impedance at this node, I have lesser calculations, and simply I can add this impedance which I am calculating as a small rn to my capital R1. That is nothing but a rn from the source. Okay, so this is the point that I want to tell you. Okay, now come to the second structure. So what is the second structure? That is my non-inverting amplifier. Okay, so here is my input. Obviously we will apply a test source here because I want to see the input impedance. Okay, so again I'll mark a here. Okay, gain. So if I'm applying a test source here, then what you can see, the structure comes to be, the structure simply comes to be, this is the test vt source and there is a it. Okay, so here one can think, if you are applying a test source here in the non-inverting terminal, then simply if I'm considering this current going inside is 0, then there is no point. Rn simply is coming to be infinite. So this is the ideal case. Ideal case. Let I'm considering, okay, let there is already input impedance of m. Why I'm considering here, I want to tell you that what should be the net expression if there is an input impedance given, and what should be the input impedance when we are looking from the source. Okay, so let input impedance of m, if only m's input impedance is given, this is called the small rn, and I want the impedance, what I want the input impedance of this structure, I want the input impedance of the structure when it means who, op amp or amp, when it is used in negative feedback fashion. Negative feedbacks, I sometime I write it like this, feedback fashion. Okay, so in that case we'll simply calculate. Okay, so why I'm considering in means rn to be finite, you can see it here. Okay, so rn finite simply means, let I call this node x. So what should be the it then? It is nothing but bt minus vx by rn. So this is the one equation that I want to have this equation. Okay, now one more equation within the output is vt minus vx times gain. Okay, this is one expression. And one more thing that we can see for the KCL at node x, what we can write, vx by r1 plus vx minus, sorry, v out by r2 equal to your it, which is entering inside. Okay, this is the third equation. So if we carefully observe it, what we can see here, okay, let's say Vx to be out 1 upon R1 plus 1 upon R2 equal to IT plus V out by R2. Okay, so if I more simplified, then what you can write? R1 plus R2 equal to IT R1 R2 plus V out R1. Or this way we can write it. Okay. So now I can have the Vx, and one more relation that I have, Vx equal to from the first ITRN, or better to say minus this Vt. This is one more relation of the Vx. If I put Vx here, then what we can have? Vt minus ITRN. If I put this here, there is a IT R1 R2 plus V out. Okay, and we can see one thing here. V out also has some relation from here. We can eliminate the V out from here. So overall, after doing this much operation, or one thing that I would like to use here. Okay, so when we will simplify these things, we can have the relation between Vt by It. Okay, so which can give us the expression of the means impedance. So is this the means correct way to analyze the things? So one more thing is that what we can see. Okay, so from here we can find out the Vt by It. So we can have the expression for the input impedance. But one more thing for the voltage amplifier, the structure what we can see. So that was the thing. That is the exact calculation we were getting for it. Okay, but I will use some approximated calculation. The approximation is that we know that the Rn what this amplifier has, say some large value. Okay, in general, the Rn is a large value. Okay, so what should be the IT? IT should be the smaller current. So overall, if I look at the node X, I can ignore this current. Okay, just approximated analysis. So approximate analysis. What you can do, you can consider that IT is actually coming and coming out of the node X. Why I am doing this? Because I don't want to see any current in this amplifier input. Okay, but obviously if IT is going here, in some way it is coming out this way. Okay, due to through the Rn. So I'm considering that, let's say this value is very small. Okay, let's say IT is very small. For the time being, for my approximated analysis, so what I can say, my Vx is nothing but from the voltage division R1 by R1 plus R2. Let I should see what it comes here. So it is nothing but, I can say also beta V out. Okay. Then I can have the one relation V out equal to what? Vt minus Vx times A. If I put Vt minus beta V out, if I can have V out on the one side, 1 plus A beta equal to A Vt. So V out can be 1 plus A beta Vt. In terms of Vt, we have the V out. Okay. So now what is the relation? It equal to Vt minus Vx, which is nothing but beta V out by Rn. Okay. Yes. So what we know, V out we know. So it can be Vt minus beta A divided by 1 plus A beta. I'm just putting it. So what I did, I simply okay. I simply put V out. Okay, I put a V out from this equation to this equation. Okay. So what we can see from here, we can see from here. Okay, It equal to, if I take the Vt as a common, then what is there? 1 plus A beta minus A beta divided by 1 plus A beta Rn. This is cancelled. So from here, what I can see, Vt by It comes to be 1 plus A beta times Rn. So this is the conclusion that I want to tell you. That's why I have taken so many means here one approximation that it is very small. So I am considering that voltage division is still applicable at a node X. So my Vx is coming as a beta V out. Because for this particular structure, when there is a voltage feedback, or I mean to say, when it is a voltage mixing is happening, or in general input means general negative feedback amplifier, what we see, the input impedance of the entire structure comes to be 1 plus a beta times Rn. So why I am much concerned about this, because for this structure we must have two conclusions. If the input is here, that is a non-inverting structure, then the result is that simple. To arrive at this result, I have taken this approximation on the previous page. So what it meant to say, if my this amplifier has input impedance as Rn and output impedance as Rout, and what is the input impedance when we are looking from the source is nothing but this Rn times 1 plus A beta. A beta is nothing but a loop gain that we know. Okay, and what is the Rout? Rout is nothing but Rout divided by 1 plus A beta. So this 1 plus A beta factor is nothing but means increasing your input impedance in the negative feedback and decreases your output impedance, which is nothing but a means it is our requirement. It is our requirement. Okay. So when we deal with a voltage to voltage amplifier, and what we generally expect, that ideally we expect that R out should be 0 and Rn should be infinite. These are the general expression, general expectations. Okay, so this negative feedback is improving this, or in negative feedback is supporting us to get this. Okay, so negative feedback supports us to obtain this condition. Okay, to obtain this condition. So it is happening in general. Okay, so why it is so? Because when I have some amplifier and I want to sense the voltage, okay, this is my amplifier. If I want to sense the voltage, then what I expect generally is Rn should be very large, or ideally it should be infinite. The reason is simple, that if we are using, let's say, this is we are sensing the voltage, or if we are sensing the voltage, and what mean to say, we are simply measuring the voltage. So if we are measuring the voltage across any internal terminal here, then what we expect, that the exact voltage at this node should come at this node. Only it is possible when there is some circuit on back end, on the back side of this resistor, or when say simply element. Okay, so what we expect, there should not be any loading. If there is a loading happening, then what it mean to say, the node voltage here, which the input of my amplifier is sensing, is not exactly what we want here. Okay, so what we want here, because what is the voltage here? Okay, let's say I is here. This is my R. So voltage here is I times R. Okay, so this is the voltage we want to sense. And if I'm connecting my amplifier who want to take this much voltage only, IR at its input, and if it will provide some load, then the voltage at this node will not be this. I mean to say, if the current I is coming out of it, and what will be then this current, then the voltage will be I times what? R parallel Rn. Okay. So if Rn is some finite value, then what we can say, this impedance is disturbed. Okay, so if this is not exactly the value equal to R, if it is equal to R, then it is fine, means in that case Rn should be infinite. And if it is not exactly R, then what we desired is not equal to what we are getting. Okay, And our the aim of capturing the voltage of particular node IR is not exactly, it is some different value, because I want to amplify this IR only. I want to amplify this IR only. So my input impedance of this amplifier should be infinite, so that it is not loading its previous circuits or whatever the previously present there. And same thing, if I am detecting the R out to be some finite value, then what exactly we will get at the output is not same as what is amplified. I mean to say, if this is the amplifier, this is the input, and what we expect that we should get A times V in. Okay, okay, simply we are using a voltmeter. How we are capturing, how we are capturing the output voltage, capturing the output voltage. So how are we capturing the output voltage? Mean to say, simply we are using the voltmeter. And if we are using the voltmeter, then ideally the voltmeter should capture all the value of the voltage what is there at the output. Okay, then only we can say we are having the correct value. But if let's say the example, there is a finite gain, and due to this finite gain, the voltage I am getting here is nothing but A times the VD, and due to some finite R out, which is called a small R out, then what to speak of this voltage? This voltage V out is not exactly equal what V out we are getting here. So it is not equal to A times V in. VD I also call the V in. Okay, V in. It is not equal to that, because due to some finite current, let I should say I out, and what is there? V out is nothing but ABDD minus I out R out, or plus I out R out. Well, it is not exactly what I want. I want only this much value. ABD. I only want this value. But we are getting something else. So it is due to the finite output impedance. So ideally I want for the voltage amplifier to capture the voltage properly, input impedance should be infinite and output impedance should be 0. I think if the point is clear, then fine. If you have any confusion, you can ask, or you can analyze it by your own. And what is happening in case of voltage amplifier, why the input impedance should be infinite and why the output impedance should be 0 ideally. Okay, so I think I can deliver my viewpoint what to means I was there in my mind. Okay, so calculating of gain directly by this that we have seen, and after that calculation of the output and input impedances. Okay, so input impedances are covered here, and the output impedance is left for your calculation. When the output impedance calculation is left for your exercise, you can simply apply the test source and observe what is happening there. Okay, so because I will not cover this thing here, I will say output impedance calculation is part of your homework. Okay, so just put the current source or by the test voltage source. So we can put a test voltage source if I want, and we can observe the current, and we can also apply a test current source, and we can capture the or observe the voltage. Either way, we can calculate the impedance at any node. Okay, so this is enough for the discussion of the CTQ 12. If there is any point left, I'll try to cover in some other CTQ. Maybe some similar concepts to repeat in some other CTQs, then I'll cover there. Okay, and if still some more discussion I want to have here, I'll try in the next video. Okay, so this is enough for this video. Thank you.